Hello, everyone. Happy Monday. Before we get into where we left off in lecture last time, there was a couple of good questions in office hours today that I think it would pay dividends if we talked about, if I shared with you what we talked about in office hours. So bear with me here. We're going to do a bit of homework help in lecture. So primarily we're talking about problem set number 3, question number 2. And this was, we're told we're dealing with 16 QAM. And the question that I think was not obviously stated in the problem was what happens when we modulate up to passband. And so the picture that I would like you to have in your heads, and it was not at all clear based on the phrasing of the question, is this. So picture a transmitter where the sequence of bits comes into our 16 QAM code book. And so based on, well, how many bits will we need? I think 4. Every 4 bits, we are sending out a symbol. So a 16 QAM symbol. And I'm asking you to consider this as a complex number. So then what I'd like you to imagine, this is clearly not what's going to happen in circuitry, but it's helpful to think of this from a systems perspective, is that we split that into its real component and its imaginary component. And the real component modulates the carrier, so cosine omega ct. And the imaginary component modulates the sine of the carrier. And then before transmission, we add those back up. Okay, so I think that what was not at all clear was this process, how we turn symbols, baseband symbols, into passband waveforms. So if anyone has any questions now, let's address those. Because yeah, in office hours it was clear to me that it was not clear to you what the heck's going on. Last time we spent a good amount of time talking about the different possibilities one could have to map bits to voltage waveforms. And we ended up with this idea that Manchester was kind of, I don't want to say the best of all worlds, but it has a lot of things going for it. But what is important going forward into today's lecture especially is that these rectangles are just placeholders, right? They are, I hope that they're in your minds as easy things to draw that help us illustrate these kind of timing benefits and polarity benefits. But sending actual rectangles in the time domain is not likely going to be optimal. So, and that's what today's lecture is going to talk about is, can we do better than rectangles? And so, I mean, when anyone asks you if you can do better, first establish what the baseline is. So if we just wanted to send rectangles in time, then in the frequency domain, we'd have to contend with this sync-like form. And so I think a lot of times when we first present syncs, we say, oh, look, they're negligible after the first zero crossing. And I mean, negligible is in the eye of the beholder, isn't it? There are other sync-like waveforms that are even more negligible. So things with even faster roll-offs, et cetera, et cetera. So the takeaway is that if you do nothing but send nice, clean rectangles in the time domain, then you are going to be leaking energy into bands that perhaps you didn't want to leak into. And so if you're like, I don't care what happens to other people's bands, that's fine, but you're on the receive end, you're not really going to have access to stuff outside of your assigned channel, your band. And if you do, like build your bandpass filter to include neighboring bands, then nothing stops other people from broadcasting in those bands, so you're going to have interference. So the idea is that we are motivated to stay in our proverbial lanes, if you will, whether that is in the time domain or in the frequency domain. So I mean, if you are on Mars and you've got no one interfering with you, take all the bandwidth you like. I think the other logical thing to consider is what if we had very strict limits in the frequency domain? So, right, this picture has very, very strict limits in the time domain, but you end up leaking in the frequency domain. Time frequency duality tells us that if we do the opposite, if we have strict limits in the frequency domain, that we will be quote unquote leaky in the time domain. And so, yeah, this is not going to be the way to do it either, but it has a couple things going for it. It is strictly band limited. Great. It is not at all time limited. Okay, so if we're going to send this pulse for every bit, then we need to truncate this, right? Because we need to say bit 1 stops here and bit 2 starts here. So then the question becomes, where do you truncate? And once you start truncating, then you start losing this nice clean rectangular form over here in the frequency domain. So today we're going to try and formalize this act of truncation or timing or and all that stuff. So I'll pause here for questions on why kind of the first 2 passes are okay from kind of a 30,000 foot level, but they leave room for optimization. Any questions about what we've done so far?
What was I? So to the first attempt where you have a strict rectangular function in the time domain, you said that you can take as many bandwidth if you are like in Mars or something with no interference from other sources. If you took it like a higher bandwidth, let's just say like 2 over tau, would that like extra part interfere with another, like would it cause overlap? I'm assuming like P of T is like a 1. Let's say like in terms of binary, like it's like a 1 in one of those. And you're sending 1 0 1 0 1 0 like sure. 1 1 1. So you're saying that I'm assuming you're sending multiple rectangle functions. If you took a higher bandwidth, would those cause overlap and interfere with each other, or not necessarily? Would they be too long?
So if you're strictly limited in time here, then the receiver architectures that we've talked about, actually the ones that the integrate and dump kind of idea, or yes. If you want to think of the cross correlator, they're only going to look at the incoming signal for 1 bit period. And so okay. the problem with leaking into other bands in the frequency domain isn't so much interfering with yourself or intersymbol interference. It more has to do with if you try and push this, spectrum through a channel that is kind of low passy, then the spectrum that you start with is not going to be the spectrum that you receive. And okay. So, yeah, then in that sense, if we start to lose the high frequency components, then the thing that we receive is no longer going to be as time limited as we thought. And so then here is the problem, right? Now we do start interfering with ourselves because the echoes from the last bit are still being heard when we process the next bit.
Okay, that makes a lot of sense. Thank you.
Okay, so this one, this is animated, but it's not going to show up if we do the thing. Let's see. Did I lose you?
We are still here.
Okay. What do you see?
I see the slide.
Okay, perfect. So I want to point out that if we try and do rectangular in the frequency domain and we get sync in the time domain, this is not actually maybe as bad as you might think, because these sinks have regular nulls, right? So follow me on this kind of mind game here, that if we want to send sinks as our time domain pulses, one way to do that would be to space our bits such that they come at the nulls of subsequent sinks, right? So let's see, do I get a laser pointer here? Nope. So if we were to transmit this sequence of sinks and then sample at 0, at TB, at 2 TB, then the upshot of this is that we're actually only sampling one of our bits, even though each bit lives in the channel forever and ever and always. But if we can sample them at these strict null points where only one sync lobe is on, then technically we can achieve 0 intersymbol interference. You see that? Because if all I ever look at the channel, if all I ever look at my receiver is at integer multiples of TB, then whether it's a negative pulse, negative sync, or a positive sync, I'll be able to see just that and only that at that bit period. For all the rest of time, I'm going to get a whole jumble of infinitely many bits, technically in the future and the past, all constructively or destructively interfering. But if I look at the strict sampling instance, then, I mean, mathematically, I can get a clear picture with no intersymbol interference. Now, that shouldn't be very satisfying to you as an engineer, because among a whole host of other problems is if I want to send a bit today, I had to have started its sync pulse before the dinosaurs. Okay. And if I don't do that, if I have to compromise and say only start sending bits when I get them, then I can't send a sync, which means that I don't get these nice clean rectangles in the frequency domain. The other problem, if that wasn't problem enough, is this small text box at the bottom, is that if your sampling timing gets off, if you're not exactly at these TBs, then based on the number of bits, if you have sent n bits, you will accumulate error like a harmonic series, which then diverges. If you send more bits, you're completely hosed. Okay. Okay, so it's a step in the right direction, but it's not enough to be practical, definitely. So let's try and look for a compromise. So this is the idea that if I send a pulse in the time domain, I'd like it to be strictly rectangular in the frequency domain, but maybe I can tolerate a bit of roll-off, provided that roll-off is constrained, if you like. Okay, so things to highlight here. This is a frequency domain plot, and this is, you can think of it as an alternative to this guy, where this is a strict plus minus RB over 2 in the frequency domain. Okay, so this is an alternative to or a compromise from this picture. Where it says that I have animation here, but I don't think I have animation. Let's try it. Cool. So the idea here is that, remember back in 328 when we started talking about sampling and what sampling does to the spectrum of a signal. So if we sample, then we copy and paste the spectrum of the sampled signal every, what, RB? If you sample it at RB, then you copy paste it every RB hertz. So this was one of the first things that I cover in my 328. But we've got in this picture down here is, there we go, okay, is this picture copied every RB and in both directions. Wait for it. Perfect. And so what this line is, it's the sum. Right? If we have a good job at rolling off, right? So if in order to make this sum constant, there is a feature of this curve that it has to be symmetric about this point. Can you see that? That if I want to add this curve to this curve to ensure a constant sum, then whatever this curve loses, this curve has to gain. And so the way to accomplish that is by symmetry about the middle of the roll-off point here. So yeah, let's talk about how we can accomplish this trade-off. So what I'd like you to be looking at here in this picture is the solid line is kind of our baseline. Right? So this is the strict band limited rectangle. And if we were to try and shave off, so the thin dashes, these two figures are coupled. So the line type on the left matches up with the line type on the right. If we were to shave off this area, we would then glue it on down here. If you see that. And the motivation there is to achieve a constant power spectral density. And there are lots of ways to shave and glue that will do this, right? Any operation that kind of cuts off and then pivots, if you think about this geometrically, we're just pivoting this area down there as a way to accomplish this symmetry. You could do linear things, right? I think there's nothing stopping you from doing this, right? So take this guy and rotate it down there, and then maintain sharp angles there and there. But the idea is that sharp angles in the frequency domain lead to long tails in the time domain, and vice versa. So if we want to keep our time domain as essentially truncated as possible, we'd like to do smooth operations, smooth slices and gluing in the frequency domain. And so one of the smoothest things you can think of is a sinusoid. And so the idea is let's let this curve follow a sinusoid, but only like a quarter of a period of one. Okay. So the way that you get from these curves to this expression is a little convoluted. But I think if we take these kind of test cases and we let fx be the excess bandwidth, so for example, for this one, fx is 1/4 RB for a roll-off rate of 0.5. And so this relationship between excess bandwidth and roll-off rate is captured down here, a roll-off factor. So let's double check this. If the roll-off factor is 0, that corresponds to 0 roll-off, that means the sharpest transition, then the excess bandwidth is 0. So double check. 0R means 0 excess. And if roll-off is as the roll-off factor is as large as it can be, then that gives us fx is 1 over 1/2 RB, and so that's 2 over RB. This calls into question this 0.5 coefficient, doesn't it? Because this, for r equals 1, we should have an excess. So the excess bandwidth is not the true bandwidth, it's the difference. So let's clean this up a little bit. I think this 0.5 ought to be on top. I think this is a typo. Right, so yeah, I think this should be fx times 0.5 over RB. I think that 0.5 should be on top. Then all of a sudden this expression actually agrees with the figure. So if my roll-off factor is 1, oh no, come on, Clay. Have some common sense here, people. People, he means himself. If I rearrange this, I get fx is 0.5 times RB times the roll-off factor. Therefore, if the roll-off factor is 1, then the excess bandwidth is 0.5 RB, which is what we see here. So the excess bandwidth is the bandwidth in addition to the bandwidth that you started at. Sorry for that journey into self-doubt. Any questions about what just happened?
Is this a Nyquist theorem, like part of Nyquist, or anyway?
I mean, so it's confusing because this was Nyquist's foray into digital communications and data transmission. So it is actually called Nyquist's condition for zero intersymbol interference. But the factor of RB and RB over 2 has more to do with Fourier than it does with Nyquist, I think.
Okay.
So what we're looking at here is going to be a formalization of the compromise between leakage in the frequency domain and duration in the time domain. So as the roll-off factor increases, we see the effective time duration decreases. So, for example, these thick dashes correspond to r equals 1, and even before we get to the second null of the sink, this waveform, which is not a sink anymore, right? Because it doesn't have a rectangular transform in the frequency domain, but this time domain waveform has already become indistinguishable from 0. So, and this r equals 0, that is a true sink, right? And that's kind of what we're measuring all this against. And so, looking at these time domain waveforms, it is, I think it's pretty persuasive that there is going to be a compromise between how much excess bandwidth you require in your frequency domain versus how much you are going to interfere with the next bit coming along. Right? So if I were to choose r equals 1, then by the time I get to the second bit period, everyone else is going to be nearly 0. And so I'm going to, again, get this super sharp pulse for the second bit. Okay. Now I pay for that because I've doubled my bandwidth. But I think it's a nice formalization. And right, there's nothing stopping you from pushing this excess bandwidth even further. Well, that's not actually strictly true, because by pushing, you lose the symmetry. You would lose the symmetry, because if you push the excess bandwidth beyond a roll-off factor of 1, then all of a sudden you have to start borrowing from somewhere to the left of the origin. And so that's going to be bad news bears. So again, this is what I was talking about, picking r equals 1. And this actually leads us to, if you have done any communications modeling, or maybe you're doing this in 456, what's called the root raised cosine, or just the raised cosine filter characteristic. So the idea is, so this is, if I let little r be 1, then the expression from the last slide reduces to this. It's literally a raised cosine. Right, because I'm offsetting it by 1. And it's not truly a cosine, doesn't go on and on forever and ever, so we're also clipping at a width of RB. So if we look at this in, so what do we got here? This is, this is the reverse of how we normally do this. This is the double angle formula in reverse. Right, so this is take a cosine and then write it as the square of cosine at half the frequency. And so I'm just doing this to show you how you would get from the frequency domain. So from here to here, wait for it. This is an inverse Fourier transform. I think I asked this on a homework assignment once, and it's hideous to take this inverse Fourier transform. So, but you can do it numerically. You can approximate this numerically and see that we are going to get something that has a sink buried inside of it, but something that also has an amplitude that attenuates like t squared, but sink already attenuates like 1 over t. And so that's where we get this multiplicative factor that this sink, quote unquote sink, is going to roll off real quick relative to a normal sink, if you like. So you think, okay, why not just do that always? Well, it means that if you had spaced your channels tightly in the frequency domain, then all of a sudden we've got this spreading out. So you can get this, what's called interchannel interference, where one way to think about this is interband in the frequency domain. So right, things that used to be, if we take this baseband and we map it up to passband, things that used to be nice and siloed, if we do roll-off factor of 1, well then, if these bands were very tightly packed, then all of a sudden we start to get interference, say, between this band and the next band. So passband 1, passband 2. right? If you had a smaller roll-off, you could more tightly pack your bands in the frequency domain, but then you would have higher time interference in the time domain. So this comes down to another consideration of trade-offs. Are you more constrained in frequency bands, or are you more constrained in error rate or in data rate? I think, right? Because we could, if you really wanted to, send these in these tightly spaced bands. We get interference, and then we're going to get higher error rates because things that we sent as positive pulses are going to come back corrupted as negative pulses, not just because of noise, but because of our neighboring channels that we're trying to transmit through. So try spreading these out. You end up paying for more bandwidth, but you have fewer errors per bits sent. Questions so far? Okay, so what I have next is actually an insertion that I didn't share with you yet. And I think this is now an appropriate time to start talking about eye diagrams. Eye like the ocular organ, not the letter I. So for this, we're going to kind of go back. I think eye diagrams are helpful, but they're a little bit overhyped, if you like. So let's think about what's going on here. Let's go back to our rectangular line code. Ones get high pulses, zeros get low pulses, or negative pulses, if you like. If you were to use that line code and then view it on an oscilloscope. So this is like viewing the waveform on an oscilloscope whose scope width was a total of TB seconds and whose persistence was infinite. Scope width, so infinite persistence. Or if not infinite, then long persistence. That is a signal that shows up on the scope, stays on the scope screen for a while. Right? And so if you had that, then whenever you got a positive rectangle, you would see a positive rectangle overwritten here. Whenever you got a negative pulse, you would get a negative pulse. And then the next high bit that comes through would go high, and then it would wrap around and stay high again. Okay, so I want you to think of this as your oscilloscope screen. And I have changed the time base so that I only look at 1 bit period. This is the opposite. This is then changing the time base to look at 2 bit periods. And so maybe the 2-bit period one is a little bit easier to illustrate what's going on here. So I guess follow my pen. I'm going to go through this sequence of bits in the double the double wide eye diagram. That's not actually what it's called. I just made that up. So a 1-bit would go high, and then the 0-bit would go low, and then I would wrap around. So then I would go from the 0-bit up to the 1-bit, over, and the next is a 1-bit, so I'd go straight across, and then I'd wrap around. Then I transition from a 1-bit down to a 0-bit, go for a 0-bit, and then transition up to a 1-bit, and then over. And I think I've gotten to here so far. But you see that if I leave the persistence on, then the trail that is traced for every bit stays on screen. So if I change my line code from being pure rectangles to being shaped pulses. So down here in the second line of the figure, let's start again from maybe midstream. We can illustrate that. So this is the 1 bit followed by a 0 bit, followed by a wraparound, followed by a 0 bit, followed by a 1 bit. So this was 1, 0, and then 0, and then 1. Now, before we get on to the crazy one, let's take a moment to think about why would anyone want to do this? What is the use of setting your oscilloscope to look at this kind of signal? Well, let's say that we're looking at a received signal, and if this started at amplitude, say 1 volt, and we had to set our oscilloscope so that this was only, I don't know, 10 millivolts, then we start to see that, oh, if this peak gets closer to this peak, then it becomes harder to decide which bit was sent. Because then for the equivalent noise power, we could get a crossover, if you think about that. So certainly the amplitudes here correspond to a little bit like the SNR. So if these amplitudes are large, then we're going to have a large signal to noise ratio. What else could we draw out of here? If the crossing points are nice and tight, that means that our timing is very consistent. That is, we say that everything lasts for TB seconds, but that's not going to be exact. Maybe it's TB plus 1% or minus 5%, because our phase lock loop that we use to generate these is trying to track or has some transients. Now, what would a bit that lasted too short in a channel look like? Well, if this was TB, if this is my scope screen, then a bit that was too short would cross there instead of there. Okay. And it would then possibly lead to the next bit being, so if we just do the one screen version, this then wraps around to over here. And now the next bit, if it is truly TB seconds long, then it is going to go something like that. And so I hope you can see that we can start to visualize the compounding errors if we look at a bunch of bits overlaid on each other. And so that's kind of what's going on here. So this is, say, a corrupted, say, received signal. All right, 1s were high, vaguely. 0s were low, vaguely. This guy looks pretty good. But this one's pretty poor. And so if you start to overlay these on top of each other, it's kind of like a probabilistic mapping of how frequently do we get frowny face situations and how frequently do we get happy face situations, because the more frequently a transition occurs, the darker its trace will be on the scope. And the more infrequent, the lighter it'll be. Because you can also get kind of a probabilistic view of what's going on just based on the brightness of the pixels on your oscilloscope, which is kind of a neat trick. So this is a figure 6.26 in your textbook, and the name eye diagram comes from the fact that this is vaguely, I don't know, eye-shaped. I don't really see it, but that's what it's called. I didn't make it up. It's kind of Illuminati, actually, kind of looking. Never mind. So these are like the diagnostics that you can get from a 2-level eye diagram. So we're talking about how far this is apart gives you your noise immunity. So for a fixed noise power, we would like this to be further and further away from the zero crossing. If this is 1 bit period, and so this is not to say that the bit is starting here and ending here. This is actually more likely to be the last bit was ending here and the next bit. So this is like 2 halves kind of copy pasted onto each other. And I hope this will become evident when I set up the demo here in a second. Actually, I should start doing that now. But so like the thickness and the width of this region shows you how jittery the received signal is going to be. And jitter is in just where the bit period it lies in time relative to each other. So if this is super clean, so if we have just these traces that look like this would be no jitter. But if we end up with kind of much fatter crossings, then, and you could actually measure this on your scope, right? You could use your cursors to determine what's the jitter timing. This doesn't tell you how to fix it, but it tells you, it's a diagnostic tool. It tells you what is the current state of the system, and it's up to you and or your bosses to decide, is that good or bad, or do we need to fix it? Okay. Okay, so let's switch over to a demo, unless there are questions on this. Okay. Share. Let's do the whole screen. Okay, so I have a random bit generator set up here on an analog discovery. If you'd like to, so question, can you see the yellow waveform here? Okay, get a couple nods, good. This is a custom waveform, and it's pretty darn simple. I'm just taking the sign of a random number that I've shifted down by a half. Okay, so, and I'm doing this 1,000 times per period. So it's not a truly random signal because it does repeat itself over time. But I think it'll be random enough for us because all I really want to show is these 1 to -1 transitions. So this ought to be a nice square eye diagram. Right, so we say that the quality of your system is measured by the opening of the eye, and so that purely rectangular eye is as good as it can get. Right, that's no compression this way, no compression this way. Everything is nice and living at the bounds. But I think what we'll see is if I drive the analog discovery up to its upper end of data rate, we'll actually see some degradation of the signal. So I'm going to repeat this every millisecond. And so what I'm getting is 1 megabit per second of modeling data, right? Because every period has 1,000 samples. So I get 1,000 bits per period, and I'm running this at one period is 1 millisecond. Okay, so let's run that. Oh, and I'm just shorting the function generator positive to the scope positive and the function generator negative to the scope ground. So the channel here is 10 inches of 22 gauge wire. Okay, so it's the best I could do without being in room 113, I think. So let's go over to the oscilloscope. So I'm going to try to dial this in the way that I would, just to show you the method. So if I've got 1 megahertz, then that's 1 microsecond per period. And so then that means I need, I think it's 20 No, I need to go one further. So 20 nanoseconds per division. Or is that too far? Okay, let's turn off channel 2. Let's, yeah, I went too far. 100. Okay, yeah, this will be, yeah, that'll be good enough. Okay, so this is what, 5 microseconds total. And what I want to do is I want to turn on persistence. And then the reason that this is, so here you're starting to see the jitter, actually, even in the little bitty analog discovery at 1 megahertz, it is not doing so well, right? So we should have 1 microsecond per bit, quote unquote bit, and you're starting to see the jitter here. The reason that everything looks so super consistent in the middle here is because I'm just triggering on the rising edge, and the rising edge is, if I do either, there we go. So now I'm starting to see down here a better eye diagram. So now I think I can actually zoom in a bit. So let's go. There we go. So this is almost like a 2-bit eye diagram. So let's see. Yeah, that's good. Okay, so what are you seeing, or what am I seeing? How can I articulate this to you? Let's start drawing on my screen. So first off, we are seeing every possible bit transition, right? So this line is like a 1 followed by a 1. This line is like a 0 followed by a 0. This curve is a 0 followed by a 1, and then this curve is a 1 followed by a 0. And so we're seeing, and this right here is the proverbial eye. Okay, so you're seeing that even with like no impairments whatsoever, no intentional impairments anyway, we are starting to see, and this is probably not super surprising to you, a low passy type characteristic. That is, things that ought to be nice and rectangular are losing some of their edge, so to speak. But not so much that if you were to try and sample this, say here, this is, yeah, you would not make any bit errors, right? Or the noise would have to be very large in order for a bit error to occur. Okay, so I think if I drive this faster, we'll see more and more errors. Let's try that. So go back to here, clear that stuff. Okay, so if I push this to 1 gigabit per second, then I suspect, well, we're gonna have to zoom in real far. So that was, I don't know if we're able to go that far. Maybe that was too far. Let's go, yeah, let's go there. So this is now 100 megabits per second. And let's clear channel 2 by changing, I don't know, changing the voltage. So I think what we're seeing is that we're running up against the bandwidth of this device, is that we're asking it to do 100 gigabit type data rate. And so then the eye opening, this is like sending a high bandwidth message through a low bandwidth channel. So we end up with a much narrower eye opening. Yeah. So this is, I mean, I've essentially invented a channel impairment by just pushing the data rate beyond what the little chip here on the analog discovery can do. And so we're starting to get a whole bunch of timing jitter. Right, so now things that ought to have been lined up well in time are not. So it's not just the low passiness of the system, it's also the fact that we're losing some timing here as well. All right, this is clearly not a bona fide RF example, but it does illustrate the point that if you try to push a high bitrate signal through a low bandwidth channel, you're going to have a bad time. Okay, that's your revelation for today. Okay, we'll wrap up this module on Wednesday and talk about frequency division multiplexing then as well. Thanks, everyone.